requested you to come to class today with a pen and a paper because we'll be doing some writing today since we won't be able to find.
Prof, please unmute yourself, sir.
Yeah, yeah, that's fine. So can you hear me now?
Yes, I can hear you.
Okay, good. So I said good morning, everyone, in the first place. And secondly, I was saying that I requested the course rep to inform you that you come to class today with a pen and paper so that you'll be able to do some writings too, since you'll not be able to find everything that I will be talking about today and even in future on this slide. The slide is just to guide you, and you need to go back and do some homework. Yeah, so we are going to continue on. Yesterday we were able to look at, or the topic generally is the ecological effect of chemicals in the environment. And we agree that these chemicals that we deal with on daily basis are also matter, and it became very important for us to know what matter is, and we're able to identify different kinds of matter. We were able to also look at some of the classification of matter. We went ahead to look at the different states, changes of matter, and we all agree that in as much as the knowledge we had before now in secondary school or primary school, that matter exists in 3 states, we saw that there is a 4th state of matter. And that 4th state of matter is known as plasma, and we're able to explain what plasma is. We looked at the changes of matter, how it changes from solid to liquid, liquid to gas, and so on and so forth. I was also able to, or I attempted to explain how the temperature, there is that possibility that the gases will become ionized. And we were told that the plasma is composed of ionized gases and what? Free electrons that have high energy, and they are able to also conduct electricity, kind of. Okay, that was what we said. We went to also look at the chemical essence of life on Earth, and we agree that there is nothing on Earth that is not made up of chemicals, including the water, including the air, including the land, including the plants, animals, and even human beings. Okay, we saw that truly life cannot be complete without these chemicals, but as long as they are in the right proportion. It is not when they are not in the right proportion. It is when they're in the right proportion that they make meaning or more meaning. to life. We also look at the abundance of some of these chemicals or elements in the earth crust and the earth generally. We're able to differentiate, okay, from these two, the earth and the earth crust. Hello? That was the much we did. Hello?
We can
Hello?
hear you, sir.
Okay, so I asked a question that I'm sure that was the much we did, irrespective of the network challenge. Now we want to continue, or we are going to continue. And what I want us to know is that we need to respect chemicals. We do not need to be afraid of chemicals, because most of the chemicals that we use are used for good. They're used to make our lives good. They're used to make our lives safe. Some of these chemicals include drugs. Drugs. We know that drugs are chemicals, but in the right proportion, they are able to bring about healing. They are able to cure, ailments. They are able to cure diseases and so on and so forth. We have plastics. We know that plastics, we can make them, into chairs. We can make them into cups. We can make them into many, many good products that will serve humanity. We also have preservatives. You know that without these chemicals, like preservatives, it will not be proper for us to, feed on some of these products that we make use of. You look at yogurt, for instance, you look at other products that we consume. If they do not have preservatives, then it means the shelf life may also be very short and will not be able to eat them, for a long time. We have sweeteners, we have cleansers, in form of antifungal, anti insects, and so on and so forth. And we have cleansers that we use in cleaning tabletops, cleaning our glasses, cleaning tables, and so on and so forth. And then we have antiseptics that are used in soaps. And we have dyes. Dyes are also chemicals. The good use of dyes. We use them to dye our clothes and so on and so forth. To have cosmetics. We use cosmetics, in creams, or like creams, and so on and so forth. We have other personal care products, even agrochemicals. We use them, in improving agricultural yield. We have a number of them. We have fuels, even the fuel that we use in our tanks, in our cars, they are chemicals. We have fire or flame retardants. Without them, we will not be able to contend, fire outbreak and so on and so forth. And coolants. We have coolants in our refrigerators. We have coolants in our air conditioners, and so on and so forth. So these are, a cocktail of chemicals that make our lives, good. Hello, are you with me? Are you with me? Hello? Are you hearing me? Okay, I hear him. Okay. Okay, that's fine. Okay, good. Right. So let's move forward. So some of the chemicals, however, they do not only fulfill their end use and could also pose risk if not handled properly. I say that when you don't use them in the right, manner, in the right perspective, you discover that they will become, a problem to us. They could pose a lot of risk to the environment and even to humanity. Unfortunately, we are told that this has perpetuated chemophobia. What do you mean by chemophobia? Chemophobia means fear of chemicals, okay? And across generations. Anyone, when you hear about chemical, the next thing is fear. But when we use them, when we handle chemicals properly, we have no cause to fear. So we need to respect them. That's all. We don't need to fear chemicals. So we live in a chemical world. That is the truth. We all live in a chemical world. So chemicals, like we said before, could be of natural state or could be synthetic. Synthetic in the sense that you can produce them. You can manufacture them in the lab and so on and so forth, in as much as they exist in a natural way. So they demand our respect, right? Knowing and treating them right can help keep us safe instead of us being afraid of the chemicals. Now, in as much as we are saying that these chemicals are for good, like we said, that is when we use them in the right perspective. And that doesn't mean that they do not have negative consequences. They have negative consequences. When introduced into the ecosystem, like air, water, soil, and food, they could lead to contamination. They could lead to pollution, right? They could lead to destruction of aquatic life, wildlife, vegetation, and may also have adverse global effect on the climate. Okay, they could lead to climate change. So when you introduce these chemicals into the environment indiscriminately and uncontrollably, what you are doing, you are, causing pollution, or that act may lead to pollution. I'll give you an example. You know, the ethanol industry or company that is along Boko Road here, that they say is Otom's company. That company was releasing their effluent. What do I mean by effluent? That is the waste that is generated from the industry was being introduced directly into the river where, that company is established or situated. And what they did, they constructed a channel underground that was, discharging the effluent into the river. And you know what happened? For those of you who heard about the story or read about it, the fishes around that area were dying. And the people who were around the place began to perceive a certain order and color change of the river along the coastal area. It was at that point that alarm was raised, So those wastes are made up of heavy chemicals, heavy toxic chemicals, and they were able to kill aquatic life. They were able to kill the fish or the fishes that were in that area completely. So these chemicals can also cause socio-economic damage. Here, ecosystem damage can lead to reduction in land and water usability for agricultural production. And where water that is used, for instance, for irrigation is completely polluted or is completely damaged or contaminated, it is going to affect agricultural production. And if it affects agricultural production, that farmers will also face a lot of challenges, and their socioeconomic, life will also be affected. It can also cause health risk. These chemicals, they pose a lot of health risk, ranging from acute or chronic risk. We are going to look at some of these things later as we move into the course. We'll look at acute, we'll look at chronic, and so on and so forth, risks, as the case may be, to our health. So many factors determine whether we will get harmed from contact with chemicals, but the dose is probably the most important factor. So you may be exposed to a particular chemical that appears to be dangerous, that appears to be toxic, but if the dosage is not up to the concentration, or is not up to the value that will cause damage or that will cause effect, you may not experience it. So that is why we're talking about contact and dose. So the dosage is very, very important. The contact time is also important. The frequency is also important. So the most important factor we said is the dosage, right? So the principle of Paracelsus says that there is no substance that is not a poison. That is what that principle says, that there is no substance that is not a poison. The right dose differentiates a poison from a remedy. So that could form an exam question. I will ask you that there is no substance that is not a poison. The right dose differentiates a poison from a remedy. Discuss or justify that statement. Hello? Hello?
With you, sir. We are with you, sir.
You are with me, right? Good. So I need that feedback. At least the class rep should be unmuted so that will serve as a feedback to me. It's not every time that I will go checking messages and so on. It distracts sometimes. Right. So we live in chemical world that, like we said, so these chemicals, be it natural or synthetic, they demand our respect. And we say that knowing and treating them right can help keep us what? Safe. Now, what are the physicochemical properties of these chemicals? What are the physicochemical properties of these chemicals? Mind you, we are looking at ecological effect of these chemicals on the environment. And the question is, what do you mean by ecological? What about ecology? Or we may even start. I would have asked that question earlier, but it is not late. You know that ecological is coming from ecology. So what is ecology? Those of you who did biology, let us pause here a bit and then get the meaning of ecology, get the meaning of ecological, and so on and so forth. Because there are some people that if you ask them the meaning of this course, they may not be able to tell you. Because the course is ecological effect of chemicals in the environment or on the environment. Okay? So what do you mean by ecology? That is where ecological is coming from. So any idea? Any idea? Any idea?
If you have an idea, just raise your hand up and you'll be granted.
What is ecology? Okay, Julius, Musa.
Yes, good morning.
Good morning. Please go ahead.
It's defined as the study of the interaction between living organisms with their non-living environment, sir. Right. Thank you.
So we can say that the chemicals are non-living, is it also? Is it also? And they are interacting. We are interacting with them, right? Yes. Dofan, Miriam. Dauphin.
Ecology is the yes, sir. I
Go
said
ahead.
ecology is the relationship between organisms, that is plants, animals, and microorganisms in the
Relationship.
environment.
That's okay. That's okay. That's okay. Right. So ecology is a study that deals with the interactions, okay, between organisms and their environment. That is what ecology is. So what it says to address or look at are the relationships that occur between living things. Here, plants, okay, animals, and non-living things. So that is what we are talking about. So these chemicals, we interact with them. Isn't it so? We interact with them. They interact with the environment, and that is correct. So when you say ecological, you are referring to anything that has to do with or that is related to interactions between organisms and the environment. So I think that has given you an idea of what this course is all about. Thank you very much for your contributions. Thank you. Right. So we are trying to look at the physicochemical properties of these chemicals. And when you are talking about physicochemical, physical means it's coming from physical, okay? Is physical, physicochemical, physicochemical, that is physical and what? Chemical properties. That is what we mean by physicochemical. And the physicochemical properties or properties generally refer to the behavior. As a human being, you have certain properties that one can use in describing you. Maybe you are someone who is quick to anger. You are someone who does not make jokes or crack jokes. This can be referred to as properties or your properties, which is a behavior, right? That behavior can be used to characterize you. So if you're someone who is easily angry, anytime they see somebody that is angry, they will be thinking that it is you, because it is you who is always angry. So these chemicals too, they have a particular way or different ways in which they behave. And these ways help us, scientists, and so on and so forth, to distinguish them from one chemical to another. So I said properties refer to the behavior of different kinds of chemicals that enable us to distinguish one chemical substance from another. There are some chemicals that undergo combustion. There are some chemicals that react with certain substances to produce certain products. So when we see a particular product, we can infer, we can suspect that, oh, maybe it is because of the presence of this, because it is this particular that reacts with that one to produce that particular product. So we use behavior of chemicals to characterize them. We use their behavior to distinguish them, right? So it is through these properties that we find uses and applications of the chemicals. There are some chemicals that when you apply them, they can stay for a very long time, or if you introduce them into the environment, they can stay for a very long time, which means that maybe they have a large or a high half-life or something like that. So they can persist in the environment. So we can characterize them based on the way they behave generally. So the physical hazards and environmental fate What do you mean by physical hazards and environmental state here? The physical hazards are the likely negative effect or harmful effect that this chemical can manifest. And then environmental fate has to do with degradation, transport, and how they persist in the environment. And the capacity of a chemical to interfere with normal biological processes are determined by its intrinsic physicochemical properties and the system with which it is what? Interacting with. All right? So there are certain intrinsic properties them based on that, and the manner or the way in which they also interact with the system or with the environment can also be another way of distinguishing them or characterizing them. Are you following?
We are following, sir.
Hello. Thank you. So
yes, sir, we are with you, sir.
Also, right. So this table is trying to show us the differences between physical and chemical properties. So when you say a material has certain physical properties, they may fall under this heading. If you say they have chemical properties, it will fall under that heading. So a physical property can be observed without bringing a chemical change. Now, we're told in SS3 and even SS1 chemistry that a physical change or a physical property does not lead to a chemical change. Now, take for instance, if you dissolve salt, table salt, take a table salt, the one that we use in the kitchen for cooking, and you introduce it into water, and it dissolves completely. And at that point, it has become a solution. You will not be able to differentiate the water from the salt, except to taste it. But that kind of activity is not a chemical change, but it is a physical change. Why is it physical? It is physical because in as much as the salt has dissolved in that water, it is not producing any new product. By the time you evaporate that water, you are going to retrieve your salt back. So in that case, there is no change. Do you understand? In that case, there is no change. So a chemical property can be observed or measured when a substance undergoes a chemical change. So when a reaction takes place, and that reaction is able to produce new products completely from the original reactants, then you can say it is a chemical property. Now, take for instance, if you burn a firewood, do you get firewood back? No. What you get is either ashes or charcoal. They are not wood. They are not firewood. So in that case, it is a chemical change because new product is produced or is generated entirely. So no chemical reaction is needed here. For physical properties, no chemical reaction is needed. But for chemical properties, a chemical reactions are needed or needed to be conducted. And for physical properties too, for those of you who are chemistry inclined, we talk about bonds here. Okay? Physical properties, they are not related to the chemical bonds of a substance because the bonds are not changed. The bonds are not destroyed. The bonds are not converted completely. But in a chemical change, the bonds break. So when they break, they form new products with new sets of bonds, kind of. And they are also used in identifying or describing a substance. They are used to predict how substance react. For chemical properties, they are used to predict how a substance react. But physical properties, they are used in identifying or describing the substance. And there are some examples that are under the molecular weight, boiling point, melting point, freezing point, volume, density, texture, color, and so on and so forth. Then under chemical properties are radioactivity, toxicity, flammability, acidity, or basicity, or oxidation state, and so on and so forth. Now, these chemicals can also exhibit what is called intensive and extensive properties. Intensive and extensive properties. They have extensive and intensive properties. Then what is an intensive property of these chemicals or substances? Intensive property is magnitude independent. Extensive property, we are told that they are magnitude dependent. They depend on magnitude. Intensive property does not change size, but extensive properties change size. Intensive property cannot be computed, but you can compute extensive property. Examples are under the table, and I'm sure they are quite clear. You can easily identify an intensive property, but extensive properties are difficult to be identified. They are not identified so easily. So we have examples of intensive properties. They include melting point, color, ductility. Ductility has to do with how strong or weak a material is. Conductivity, pressure, boiling point, freezing point, odor, density, concentration. These are examples of intensive property. But under extensive property, you have length, you have mass, you have weight. You know that you can calculate weight, volume, surface, area, energy, and so on and so forth. Hello.
Well, with you, sir.
Right. So I think these examples have buttressed what intensive and extensive property are. So you need to know the differences, because I may ask you in exams to differentiate between intensive property and extensive property with examples. So it's a good example. Now, what are the classificatory criteria for chemicals? What are the classificatory criteria for chemicals? There's criteria for classification of chemicals. There's criteria for classification of chemicals. And the first criteria is the periodic table. Periodic table is the first criteria. If you go to the periodic table, you see that the elements are classified. There are some that are classified as rare earth metals. There are some that are classified as earth metals. There are some that are classified as actinized, and so on and so forth. There are some that are radioactive in nature, and so on. We can also classify these chemicals as natural or synthetic. Okay? We classify them as natural or synthetic. Another one, can calculate them can classify them based on their chemical nature. Their chemical nature, like raw or mineral, organic salts, petrochemicals, corrosives. The corrosives are materials that are highly reactive. They're very, very toxic. Okay? And then we can also classify them under specific elements, okay, that is present, like oxides. You can have something like calcium oxide, okay, like hydrides, halides, organic, inorganic, organometallic, okay? And then the type of bonds too. You can also classify them based on the type of bond that is present in them. So you have ionic bond, you have covalent bond, you have coordinate bond. All right? So the kind of bond that you find in an element will also serve as, a basis for classification. Very, very important. Reactivity. The acids are highly reactive, corrosive, compared to bases and salts. And then based on redox reaction. We can also classify them based on uses and application. There are some chemicals that are used for this particular purpose or that particular purpose, or based on application. We can also classify them. We can also classify them as hazardous and toxic, based on their toxic nature. There are some that are highly toxic, there are some that are moderately, and there are some that are non-hazardous or non-toxic completely. So this is the basis, okay, of classifying these chemicals. That's the periodic table. If you look down on your right, you see the color code. It's not very clear, but the first one is talking about metal, metalloids, non-metal. Okay, metals are solids, metalloids are liquid in nature, non-metals are gaseous in nature, and so on and so forth. So that's a typical way that we can, classify these elements, like the periodic table. Okay. Then, like we said, these chemicals are hazardous. That is when they are used inappropriately. And it is good that you also have an idea of how they are coded. So what you are seeing here is referred to as the hazard diamond. Hazard diamond. So the 4 that you are seeing there is indicating deadly. Deadly. So if you see a particular chemical that is labeled, maybe with a red color, all right, and is indicated as you are seeing here, maybe 4 in that red color, the first thing that comes to mind is that that chemical is what? Deadly. So you must be very careful with such a chemical. So if you see 3, which is blue, right, you know that it is extreme danger. Extreme danger. If you see a yellow with 2, you know that it is what? Hazardous. And then 1 is slightly hazardous. And when it is a 0, it is a normal material. It means it cannot cause any harm. So that is how these chemicals are classified in terms of hazard that they can cause. Then you can look at the flash points. If you look up, flash point, you know what I mean by flash point? That's a point at which there's the minimum temperature at which a material or a chemical or a substance can cause fire or can produce fire or can ignite, something like that. Okay, so you see 4 below 73 degrees Fahrenheit, 3 below 100, 2 above 100, not exceeding 200, 1 above 200, and 0, it means it will not burn. Okay, when you see that, these classifications, you should be able to understand them. Then they can be classified in terms of reactivity. That is fire hazard. Here is head hazard. That reactivity. Okay, if it is 4, it means it may detonate. You know what I mean by detonate? Like ID improvised these explosives. It provides explosive device, kind of. So if you see 4 on such materials or products, then you know that it may detonate. It may detonate. Then 3, shock and heat may detonate. That is, if you apply heat to such materials, you will trigger them to detonate or to cause detonation. Then you have 2 is violent chemical change. It can change in a violent way or it can produce a violent reaction. Then 1, it is unstable if it is heated. And then 0 means the material is what? Is stable in nature. And then you have a specific hazard. When you see OX, it means it is an oxidizer. An oxidizer. If you see capital ACID, is an acid. If you see capital ALK, is an alkali. That is a base. If you see capital COR, it means it is corrosive. Then you see W with a line in between that you should use no water. It means that material may react if you introduce water to it. So you don't apply water to it because it may cause a violent reaction that may lead to a very serious human risk. And then when you see the one that is in form of a fan, then it is a radioactive material or a radioactive substance. I know that radioactive substances are very toxic. They are spontaneous because they react spontaneously, and they do not, sometimes they do not require any external force or heat to react. They could react on their own. That is spontaneous reaction. And so when you introduce heat, they could also react, disintegrate, uncontrollably. And you know that they are used for treatment of certain ailments in the hospital, and as well as the power stations, radioactive power stations to produce electricity or generate heat, and so on and so forth. Okay, are you following me?
We are following, sir.
Right. So we are still on the ecological physical-chemical properties of these substances. So physical hazards and environmental fate. I mentioned that earlier. I said it has to do with the degradation of these chemicals. Now, some of these chemicals, when they enter into an environmental compartment like soil or water, how do they how do they degrade? How fast do they degrade? How long do they stay in that environment? That is what we refer to as environmental fate. You agree with me that the longer these chemicals, as toxic as may be, if they persist in the environment, then it means they can cause more harm than when they just stay maybe for a very short time and are converted maybe into a harmless product or harmless material, right? So that's what we're referring to as environmental fate. How do they degrade? How long do they stay in the environment? Do they stay for a very long time or short time, and so on and so forth? And the inherent hazard of a chemical such as its capacity to interfere with normal biological processes are determined by its, we have said that before. And for organic and inorganic chemical, these intrinsic properties are determined by molecular structure. So the extent to which these chemicals may cause harm or may even interact with the environment, maybe, yes, even during biological processes, depends on the structure, depends on the structure, the molecular structure. While for other materials, they could be determined by the composition, size, structure, and morphology. So you can, if you look at the morphology of certain materials, you should be able to tell what kind of reaction or what kind of effect they might cause. If you bring a material, a substance, or you bring a molecular structure of a particular substance, looking at it, you should be able to tell if you have it, if you have a particular substance or maybe chemical that has a lot of chlorine on it, that will give you a message. Or has a lot of carbon, or has a lot of branches or chains, it will tell you. Okay? Or if you are able to know the composition or the size of that material or that substance, that will also help you, or he has helped you to know whether that material is going to have a detrimental effect, either in the environment or human, and so on and so forth. So, like for instance, if you take for molecular structure now, a material or a substance that has a large molecular structure will take a bit of time before it may be broken down. So by knowing the structure, you can tell that this material can persist in the environment for a very long time or a short time. Okay? So these physicochemical properties can, as we have said before, can be used to predict environmental fate. If you are able to predict environmental fate, you can predict toxicity or ecotoxicity, of the chemicals. Because if you have a chemical that persists in the environment for a very long time, then toxicity is likely to, to be high, or ecotoxicity, okay, will likely to be high. So that is how you use these physicochemical properties or parameters or characteristics to, predict the fate of these substances in the environment, so on and so forth. So this is just giving you an overview of types of physicochemical properties and the relationship to environmental fate, biological and ecological processes, and toxicity. So you have physicochemical properties, you have physical properties, you have solvation properties. Solvation has to do with dissolution, how they can dissolve. If you have a material that dissolves so easily, then that will also have an implication on the environment. Isn't it also? You have a toxic substance that can dissolve so easily, that can go into solution so easily. Then you should know that that material or substance can be transported very easily too, right? Then you have some other molecular attributes. Okay, all of these affect or are used to predict environmental fate. Okay, in biological and ecological processes. Okay, and from there, it can lead us to what is called can lead us to other properties or characteristics like bioconcentration, biodegradation, bioavailability. We are coming to that. And then you begin to look at human toxicity, how they affect the human, how they affect the plants and so on and so forth. Right? Hello? Hello?
We are with you, sir. You are in
Right.
power, sir.
Thank
Yes,
you.
sir.
So now, this is just kind of clarification on what you saw. What I mean, what you saw is this. Okay? So physical properties. So what are the physical properties? They include freezing point, boiling point, melting point, infrared, spectrum, electronic parameter, viscosity, density. These are some of the physical properties of electronic parameters, molecular weight, boiling, freezing, just repeating. They are directly associated with environmental fate and health effects. Viscosity has to do with how thick or loose a material is it also? Density is how maybe heavy a material is. So if you have a substance that freezes so easily, or boils easily, or melts easily, it will have an implication on the environment and even health of humans, and so on and so forth. Okay? Then you have solvation properties. Solvation properties. We are here, physical properties, solvation, and so on and so forth. Solvation properties. I asked the rep to forward this material to you, this slides to you. I'm sure he has done that. Ongo, you did it. You did it, right?
Yes, sir. I've shared the material.
And the other material sent to
Yes, the link.
The link. You will find it interesting when we get to certain aspect of the lecture, because they are not captured so well here. So if you read that material alongside what we are doing here, it will help you. That's okay. People are saying that they are hearing me. They are hearing me. Everybody is saying hearing you, hearing you. That's okay. That's okay. IED, yeah. It provides explosive device, like nuclear power stations. That's okay. Okay. Right. Thank you very much. I'm happy that you are all hearing me. So, when you talk about solvation properties, what are you saying here? Solvation properties. What are you saying here? Solvation properties describe chemicals interactions with different phases. Okay? They describe chemical interaction with different phases. And its partitioning between phases. We are going to look at that. I hope you will appreciate. Solvation properties of interest are phase partitioning, solubility, and colligative properties. We're going to look at that shortly, in detail, shortly. So I said they describe interaction with different phases and the partitioning between phases. For instance, you may have a substance that is in the midst of maybe two immiscible or semi-immiscible substances, like maybe oil and water, or organic material and aqueous material. So in this case, you may have an aqueous phase, okay? You also have an organic phase. And then the chemical is in between these phases. That is either organic phase or what? Inorganic phase. Now, the distribution of this material in the phases, be it organic, be it aqueous, is what we are referring to as partitioning. Because when the material enters the two phases, it is going to partition itself. Some of it may be in the organic, some may be in the aqueous, or all of them may be in the organic, or all of them may be in the aqueous. And they have implication. They have implication. We are going to look at that shortly. So that has taken us to phase partitioning. Phase partitioning. And in phase partitioning, the factor or the quantity that we look at in phase partitioning is what is called partition coefficient. Partition coefficient or distribution coefficient. These are the parameters that we look at in describing phase partitioning. So what do we mean by this? It's defined mathematically. That is why I said you should bring pen and paper today. We are about entering that time now. If you didn't bring pen and paper, so that one is your own palaver. It's not my own palaver. Right. So we're looking at partition coefficient as a factor that is used to predict fate of these chemicals in the environment, kind of. So a partition coefficient or distribution coefficient is defined mathematically as the ratio of concentration of a given compound. Now, get this right. When I mention or when we mention a compound here, it's as good as a chemical or a substance or matter. We have said it before. So it is the ratio of concentrations of a given compound across two mixed immiscible phases at equilibrium. At equilibrium. Though partitioning can be measured across a range of solvents and phases, the phase partition coefficient most often encountered when assessing physicochemical properties is from a system where one solvent is water or aqueous. I mentioned that before. One solvent is water or aqueous, or is in the aqueous phase, and the second is what? Organic and hydrophobic. Hydrophobic. Now, what we're talking about here is this. For instance, you have octanol. Octanol is an organic material with what? Water. All right? Then the partition coefficient is given as KOW, which is represented by P. So now, partition coefficient, as you may see on the screen, is equal to the concentration of that material or substance or chemical in the organic phase divided by the concentration of that chemical. The capital C you are seeing is concentration of that chemical in the aqueous phase. Now the chemical has entered the organic and aqueous phase. It is going to partition is going to distribute itself in the organic or aqueous phase. So where C, organic, is concentration of the chemical in the organic medium or organic phase. And the capital C, aqueous, is concentration of the chemical in the aqueous phase or aqueous medium. Do you understand? Hello? Hello?
We are with you, sir.
Are you understanding me?
Very well, sir.
Now, let me read another definition of partition coefficient that I have here before we continue. Then I will make a statement thereafter. Partition coefficient is a measure of how a chemical distributes. Can you hear that? Distributes itself between two immiscible liquids. Now, what are the two immiscible liquids here? The organic solvent and what? The water. The water here is mixed with the organic. But you know that water and organic material does not mix completely. You will see the organic on top, you will see the water under because of the difference in density. So hear this very well. Partition coefficient, also known as, well, as P or something, is a measure of how a chemical distributes itself between two immiscible liquids, like oil and water. In this case, they say like oil and water. In environmental science, sorry, like oil and water, full stop. In environmental science, it is a big deal because it helps predict how a chemical will behave in the environment. Now, let me tell you the significance of this partition coefficient. The partition coefficient tells us, you can write if you like, how likely a chemical is to accumulate. It tells us how likely a chemical could do what? Accumulate. It tells us how likely a chemical can accumulate in living organisms. How it can accumulate in living organisms. That is bioaccumulation. That is bioaccumulation. For those of you who are writing, can I continue? Hello?
Fire on.
Number two, it tells us how a chemical will move through soil and water. It tells us how a chemical will move through soil and water. If you are able to know how a chemical will move through soil and water, definitely you should be able to predict whether that chemical is capable of contaminating groundwater or not. Is it not so? So it also tells us its potential That is the potential of that chemical to contaminate groundwater. To contaminate groundwater. And it will also tells us how it will affect the different environmental compartments. That is air, water, soil, and biota. Now, let me give you one example. If you have a chemical in the midst of these two immiscible solvents, and a chemical is more inclined to the aqueous phase, what will be the implication? And if the chemical is more inclined to the organic phase, what will be the implication? In maybe soil, in the soil, for instance, what will be the implication? Or maybe in the human body, what will be the implication? Any attempt? Can any of you attempt that question to answer it? You have a material that is being distributed into the organic phase and the aqueous phase. The aqueous phase is that water, is the water I'm talking about. Now, if you have more of it in the organic phase, distributed in the organic phase, what will be the implication in the human body or in the soil, for instance? And if you have it, you have more of it in the aqueous or inclined to the water phase, what will be the implication in the soil or in the human body? Can anybody answer that question? Hello? Hello?
You can just raise up your hand so that
okay, all right. Okay, Wange has his hand up. Yes, Wange, can you speak?
Yes, sir. Good morning, sir.
Good morning.
Thank you for the wonderful chemistry you are bombarding us with this morning. Thank you very much.
Thank you. I know that you will not run away after this one, because you are over 149. I mean, yeah. And at the end of the day, I hope I will not have only 20 people left.
Can I go ahead?
Yes, go ahead.
All right, thank you, sir. I would want to try based on what you have said. You have said that there are two properties involved here. One is aqueous phase and the other one is organic.
Yes.
So if a substance or a chemical is so much inclined to the aqueous phase, which means its ability to dissolve in water, it means it will be readily soluble in water, and it will be transported by water as such through that environmental media.
Maybe through runoff and so on and so forth.
Through runoff and all that, when it comes to agrochemicals.
Leaching.
Yes,
through leaching,
yeah. Yes, please. Which one of them is PFAS? Then, if you have it more inclined to the organic part, it means its ability to combine with other organic compounds that are found in that environment. You see methane or some other carbonated hydrocarbons combining with fluorine to form polyfluoroaromatic substances, like we can see in PFAS. So these are the different phases. So one will actually tell us whether it will contaminate water if a water medium is present. So the aqueous phase will tell us that. Then on the organic side, it will tell us its affinity for organic compounds.
Yes.
In that particular solution. So if it is organic,
and it is possible that
if it is organic, sometimes if it is organic, sometimes it leads to bioaccumulation.
Exactly.
In some organisms, especially in aquatic life, that are so much exposed to some of these agrochemicals runoff or residues. I think that's a little contribution. Thank you.
That's okay. Thank you. Thank you very much. Julius wants to say something too. Julius wants to say something too. Julius, can you speak? Musa?
Yes, sir, I'm with you. Thank you for the opportunity.
Jennifer, hold on. Please go ahead.
Yes, the last speaker has said it well, but then you see, even though the two, both in organic and then in in aqueous solutions, I think that
organic phase.
The both also they co-interact together, because when it is in an organic state, it is likely to go back. It is likely to happen as a result of the aqueous. So that is the contaminant moving in water, then having maybe react with the organic, to form a whole solution of its own. So they can also correlate. That's what I feel. Like, for example, in affecting, let's say, humans, like you've asked, it could be in a result of let's say food poisoning, right? Because it accumulates in the fruits which the humans consume, and then it takes a long-term a long-term reaction to be able to cause some effect, to cause some diseases, like some carcinogenic diseases like cancer on the human body. And the same thing goes with the animals. Exactly. Then when it is on land, on a media such as land or air,
soil,
or let's say on the soil, on the soil rather, it contaminates the soil by affecting the microorganisms in the soil and also other living organisms in the soil. Thank you, Prof.
That's okay. Thank you very much. Thank you. Thank you. Julius, you want to say something very quickly? Musa, can you speak? All right. So I'm sure with these explanations, I don't need to go further and begin to speak about this. But I want to say that before your exams, you are going to have a whole 1 week revision class, a whole week. And that revision is expected that all of you are physically present. So if you are physically present, you have the opportunity of me trying to explain these things much detail, in more detail, with maybe more examples and so on and so forth. So I encourage you to participate in the revision class that will come shortly before your exams. You know that you're expected to be on ground for your exams, and before that you have 1 week revision period. So at that revision time, it will also be an opportunity for us to interact much deeper. We have another one is environmental partitioning, but it's the same, it's almost the same as what we have discussed before. It's talking about partitioning, but this one is more of media specific. It's more of media specific, but it is no different. It's just telling you how, these things, if they distribute in the organic phase or they distribute in the aqueous phase, what will be the implication. So there is no difference here. So these coefficients provide insight into environmental partitioning of the molecule and the potential for bioaccumulation. I think we have explained that enough here. So we can move forward. Now, another question I want to ask, you know that if you go back to the partition coefficient, we are told that P is equal to the concentration of the chemical in the organic phase divided by the concentration of the chemical in the aqueous phase. Now, what is the significance of the value of P in terms of magnitude? If the value of P is very high, what do you expect? And if the value of P is low, what do you expect? Hello? Is anybody there to salvage the situation? What will be the implication of what will be the implication? Okay. Let's go to George. George, can you speak? George?
Good morning, Prof.
Good morning, George.
If P is high, that means there's more concentration of chemicals in the organic medium compared to the aqueous medium. Thank you, sir.
Correct.
And vice versa.
That's okay. So what will be the implication? What will be the implication? Yes, I agree with you that if the value of P is high, then it means you have more of the chemical in the organic phase. That is correct. And if the value of P is small, then you have less of the material in the aqueous phase. Then what will be the implication? What will be the implication? In terms of accumulation, in terms of persistence in the environmental media. All right, let's go to Julius again. Julius, can you speak? Hello, Julius. Julius, can you speak? Hello? Or is it Wange? Wange, that's Wange.
Okay.
Please go ahead, Wange.
Thank you once again, Sam.
Yes.
If the value of P is high, it means the product is in organic phase. And once that is in organic phase, it will lead to bioaccumulations in living things. And in most cases, causing health hazards like low response to low immune systems and all that in some of these aquatic lives. I think that's one of the effects. Thank you.
That's okay. There is another hand up here. Let's look at what Gigi has to say. Right, Gigi.
Hello, Prof. This is Julius online.
Okay, Julius, I wanted Gigi to speak. Sorry, hold on, Julius. Gigi, can you speak? Gigi?
Hello, yes, sir. I can speak. Can you hear me?
Yes, go ahead.
Oh, yeah. Good morning, sir. Good morning, everyone. All right.
Good morning.
I'm thinking that if P is very high in the organic phase, like my mate rightly said, it causes bioaccumulation, and then from there, if the substance is not degraded in the environment quickly, it will subsequently be passed through the food chain throughout this thing. So if the value of P is high in the organic phase, it means it will accumulate so much in the environment, and then the accumulation and the toxic substance will subsequently be passed through the food chain, causing various health hazards. Thank you.
Right. So you know that when the value is low, it means that it is more soluble in water. I hope you know that. When the value is low, it means the material or the chemical is more soluble in water. It will make it more likely to be leached into groundwater and so on and so forth. Right? I think we have done justice to this. I'm happy the way you have also responded. Right. Thank you very much. So let's move forward. Right. Solubility is another property. I think I don't need to dwell so much on solubility because you know that the more the material is soluble in a particular medium or in a solvent, you know the implication. So solubility refers to the ability of a given substance. That is the solute. What the solute here means the chemical. It means the compound. It means the matter that you are considering. So that is what we mean by solute. Solute is the same thing as, it could be analyte. You can call it an analyte. You can call it a solute. You can call it a chemical or a substance that you are looking for. So you can see that if you are able to identify the various partition coefficients of different chemicals, you'll be able to predict their environmental fate. Is it not so? You'll be able to identify the environmental fate. So, ability of a given substance to dissolve in a solvent is known as solubility. It is also defined as a concentration of the solute in solution when it is in equilibrium with the solid substance at a particular temperature. So temperature is a factor. It's a factor. Then we have other properties too, and these ones are called colligative properties. They are called colligative properties. Can anybody tell us what colligative properties are? And anybody tell us what colligative properties are? What are colligative properties in your own understanding? In as much as we are told that colligative properties of solutions are not dependent on the chemical species, but instead are dependent on the ratio of the number of particles to the number of solvent molecules in a solution. So these are properties that depend on the number of that material in question compared to the number of solvent molecule in a solution. That is what we refer to as colligative properties. Properties of solutions that are not dependent on the chemical species itself, but are only dependent on the ratio or the number of solute particles, the number of solvent molecules in a solution. Right? Any further clarification on what colligative properties are? And all right, Julius is there to give us more light on this. Julius, right. Can you speak? Musa?
Yes, thank you very much, Prof. From the word colligate, it means, to me, it's accumulation, right? It's telling us on the degree of accumulation of that concentrate or solute in a solution, right? So it like the words, it has nothing to do with the chemical species, but rather with the ratio, that's the number of the particles, telling us whether those particles are accumulated, are they in density, are they sparse, are they maybe by their nature of conductivity, are they covalent, are they loose like van der Waals? And then this is a simple analogy to what gave us the freezing point, hence, and then the boiling point, because it is the temperature that is acting that falls to 0 degree Fahrenheit that gives us a freezing point, and then it is the same temperature that rises to 100 degree centigrade that gives us a boiling point. Prof, thank you very much.
Right. The head of the department, I can see the head of the department here, environmental sustainability, is raising his hand. So let's give him an opportunity to say something.
Prof, I want to speak to the ecological importance of physiochemical properties.
That's all right.
Good morning, sir.
Thank you very much.
I was just passing by just to greet and to applaud what is ongoing here, sir.
That's okay. My head.
Well done, Prof. Well done, Prof.
Go ahead. Okay, he has gone off. He has gone off. Right.
Yeah, that's part of it.
That's okay. That's okay. All right. Well, he has made a point, and you know, colligative properties are physical properties. That is what I want you to first appreciate. And like we said, these are physical properties of solutions. When we are talking about solutions, it is not just you fetching water and adding salt in it, and then that's solution. These things are happening live, they're happening in the environment, they're happening in the soil, right? They're happening in the sediment, okay, environment, and so on and so forth. So it's not just when we are mentioning solution here, it's not that you are fetching water and introducing a solute into it to become a solution. You know, these chemicals, you know, they are found in the soil. And you know that the soil is also made up of different kinds of material substances, including water. And they interact with water, they interact with organic matter, they interact with inorganic materials, and so on and so forth. So that is what we are talking about here. And as they interact, you know, depending on some of these properties that they have, they could affect the environment in various ways. So colligative properties are physical properties. Someone says this is pure chemistry. I'm sure that person is not going to run away. So colligative properties are physical properties of solutions that depend on the concentration of solute particles. So they depend on the concentration of the solute particles. That is how much of the solute particle is in the solution. Okay? Not their identity, not what they are. All right? And we have a number of them. We have vapor pressure lowering, vapor pressure lowering. Let me see what guys are writing in the email quickly. Jesus. Freezing point lowering, somebody is mentioning them. That's okay. Somebody say, I don't understand what is happening here. I'm sure you will understand as we move forward. You will understand at some point. Okay? You will understand. All right. So we have these properties. We have vapor pressure lowering. We have vapor pressure lowering. And what I want you to go home with here, please take your mind away from the relationships that you are seeing on the screen. I mean the formula you are seeing here, and just listen to me, and you may even copy what I'm telling you now. For those of you who have come with pen and paper, we're talking about vapor pressure lowering as a colligative property. It's one of the colligative properties. And like we said, it's a physical one. It's a physical property. Now, What does it mean? Now, under this vapor pressure lowering, it has to do with adding solute. Or let me say, when you add solute, I've told you that that solute is also known as the chemical. It's also known as a substance, also known as analyte, it's also known as compound, as the case may be. So if you add solute to a pure solvent, it is expected, or what you will observe is that the vapor pressure of that solution will be lowered compared to the original pressure when it was just a pure solvent. All right? So adding solvent lowers the vapor pressure of a solvent. That is why you have vapor pressure lowering. That when you add a solute to a solvent, it lowers the vapor pressure or the pressure of that solvent. That is what we are referring to as vapor pressure lowering. Now, the other one is boiling point elevation. Boiling point elevation. Here is when the solution boils at a higher temperature because you have introduced a substance in the solution, and then it will make the boiling point to elevate or to elevate. All right? So when you introduce a chemical or a substance or a solute in a solution, the boiling point of that solution is elevated. And then the freezing point, depression. The solution would freeze at a lower temperature. If the solution was to maybe freeze at 0 degrees Celsius, and you introduce a solute in it, it will make it to freeze at a lower temperature, say minus something. You know that minus something is less than 0. So it will depress the freezing point. It will depress it. It will reduce it or something. And then the other one, you have osmotic pressure. Osmotic pressure is the pressure that is needed to prevent a solvent from flowing through a semi-permeable membrane from osmosis. So that pressure that is preventing the solvent to flow through a semi-permeable membrane is referred to as osmotic pressure. And all of these are properties that can be used to characterize or to distinguish these chemicals when they are in solution or when they enter a solution. So there's a relationship there that that will help us to look at some of the examples. I don't know whether you're with your paper. I want to give us example for each of these. That is relative pressure or vapor pressure lowering, boiling point elevation, freezing point depression, osmotic pressure. I don't know whether you have a paper there. I want to read and then see how we can apply these equations in real time and get value for what we are talking about. Hello? Hello? Hello?
Prof, we are with you, sir.
Okay,
yes, sir.
So,
yes, sir.
Do you have a paper, or I should forward the calculations to you? Are you be able to follow? Maybe I'll forward it to the course rep, and then you now distribute it to.
We have paper.
You have paper, right?
Yes, sir.
If you have paper, let us use this the next 20 minutes to do these calculations. You appreciate better than me talking. Yeah. When you have a practical example, you appreciate better. And from the calculations, you understand. Right. Can you write this now? We are starting with the vapor pressure lowering. Vapor pressure lowering. Right. 1 minute. Vapor pressure lowering. Vapor pressure lowering. All right. Right. Calculate the vapor pressure lowering. Are you there? Calculate the vapor pressure lowering. Calculate the vapor pressure lowering of a solution. The vapor pressure lowering of a solution made by, are you there? Calculate the vapor pressure. Calculate the vapor pressure lowering of a solution that is made by dissolving, 10 grams of glucose. So in this case, glucose is the chemical that you are introducing into the solution. Calculate the vapor pressure lowering of a solution made by dissolving 10 grams of glucose. Now the chemical formula of glucose, put it in bracket. 10 grams of glucose in bracket, capital C6, it's supposed to be subscript 6. Capital C6, H12, C6, H12, and then H12 and O, that's capital O, O6, capital O6. I'll send it in the chat. In 100 grams of water, 100 grams of water at 25 degrees Celsius, we are told that the vapor pressure of pure water, mind you, you are introducing the chemical, in this case, glucose, into a pure water. We want to see the effect of introducing that chemical into pure water on the vapor pressure of the solution. We are told that that vapor pressure will lower, or we reduce, or it will lower the vapor pressure of the solution. That's the implication. So the vapor pressure of pure water at that temperature is given as 23.76. 23.76 millimeter mercury. 23.76 millimeter mercury. I've sent it on the chart. I'll copy from there. So it's 23.76. It's not what I have written. My 23.76 millimeter mercury. That is it. 23.76 millimeter mercury. Are you there?
Mm.
No. Now, how do we calculate this? How do we determine the pressure? How do we determine the vapor pressure? The change in pressure. The change in pressure. First, you need, are you hearing me?
Yes, sir.
Yes. First, you need to determine the number of moles of the glucose. You need to determine the number of moles of the glucose. And I will show you how to determine the number of moles of glucose. You can write. Let me give you this formula. Number of moles generally is equal to mass over the molar mass. The number of moles is equal to mass over molar mass. In this case, the number of moles of glucose is equal to mass of the glucose that was dissolved divided by its what? Molar mass. Divided by its molar mass. Divided by its molar mass. So number of moles N, small n, as you can see in the formula, N is equal to mass over molar mass. So for you to get the number of moles of glucose, is going to be 10. 10 is going to divide 180 grams per mole. Moles of glucose is equal to 10 divided by 180 grams per mole. Now, somebody will ask, how did you get the 180? Who can tell us how we got the 180? Quickly. We say number of moles is equal to mass over molar mass. And we know the mass of glucose that was dissolved in the pure water. Hello, go ahead.
Yeah. Once again, good morning, sir.
Yes, go ahead.
We got the 180 as total value of the molar mass by saying 6 times the molar mass of carbon plus 12 times the molar mass of hydrogen,
yes,
plus 6 times the molar mass of oxygen, that is atom, the molar mass of the respective elements. So
yes,
if you know that of carbon to be X, you have 6 times X plus 12 times, we know of hydrogen to be 1. So
yes,
12 times 1 plus, we know of oxygen atom to be 16. So 6 to be 16, I think so, 6 times 16. So at the end of the day, you have 180 if you do the mathematics. Thank you.
All right, that's correct. That is correct. That is correct. He is correct. Then you need to also determine the number of moles of the water. Okay? And we are told that it will dissolve in 100 grams of water, is it not so? So you are also going to determine the number of moles of water, that is 100 grams, divided by the molar mass of water. And what is the molar mass of water? It's the same thing. Hydrogen is 1, that is H2O, okay? H2O, that is water. That is 2 times 1, 2. Oxygen is 16. You have only 1 oxygen there. So that is 16 plus 2. It will give you 18. So in the case of glucose, it is going to be what? 12 times 6 plus 1 times 12 plus what? 16 times 6. That will give you 180. That is for glucose. Right? Then mind you, you are going to determine what is called the mole fraction. Now look at the formula, the first formula, equation 2. The mole fraction is n over n plus n. That is the number of moles. The two number of moles, you are going to add them. The number of moles of the solute divided by number of moles of solute plus number of moles of the pure water. Did you hear me? Number of moles of number of moles of water. Number of moles of water. The one that is up is the number of moles of water. The small n that you have there is the number of moles of water. Divide by the number of moles of water. The capital N is the number of moles of glucose. The capital N is the number of moles of glucose. In this case, are you following?
We are with you, sir.
Right. So we have determined the individual number of moles now. That's the number of moles of glucose and number of moles of water. And I'm saying that the small n you are seeing in that formula is the number of moles of water, okay? And the capital N is the number of moles of the solute, that is the glucose. So you are going to determine the mole fraction now. So what is the mole fraction? The mole fraction is going to be the answer you are going to get from 100 grams divided by 18. If you do 100 grams divided by 18, that gives you the number of moles of water, small n. And then that should give you about 5.56. 5.56. 5.56. Then if you divide 10 by 180, that will give you the number of moles of the solute, which is the capital N. Capital N. 10 divided by 180 will give you capital N. That is the number of moles of glucose. So the mole fraction now is going to be equal to 5.56 divide by 5.56, that is small n, plus the answer you are going to get for glucose, which is 0.0556. So that's going to be 5.56 divided by 5.56 plus 0.0556. So when you do that calculation, you should have about 0.99. 0.99. 0.99. 0.99. So how do we calculate the vapor pressure, the vapor pressure now? The vapor pressure is equal to the vapor pressure is given as, let me say that. The vapor pressure is given as the vapor pressure of the solution is given as the mole fraction. The mole fraction in this case is what? 0.99. In this case is 0.99. The mole fraction multiplied by the pressure of the pure water. The pressure of the pure water is given as 23.76. It's given as 23.76. 0.99 times 23.76. That is going to give you 23.52. That is the pressure of the solution now is 23.52. If you multiply the vapor pressure solution, multiply the mole fraction by the pressure of the pure water, that will give you 23.52 millimeter mercury. Now, how are you going to arrive at the final answer? Mind you, we are looking at the change. So it's going to be the original pressure of the water minus what we got now. Mind you, we say that the pressure of the pure water will be more than that of the solution because we have added something into it. So it will do what? Lower the pressure. So you are expected to subtract 23.52 that we got from 23.76, which is the pressure of the pure water. And then you are going to have about 0.24. If you do that, you get 0.24, which means that vapor pressure is lowered by 0.24 millimeter mercury. If you don't understand, by the time we are doing the 1 week revision, it will be live in the class and you may appreciate it better. Do you understand? So I encourage you to be in class for the revision so that some of the things that we're saying here, and you should also be noting down the areas that you are finding it difficult. Don't run away. The areas that you are finding it difficult to understand, note them. And maybe at the end of this class, we can throw more light on it. That is by Friday. We'll try and finish early. Maybe the afternoon class, we'll do small revision. Let me say on-site revision. So at that point, we can also explain certain things. And during the revision time, some of the concepts. Okay, we have 2 minutes.
So we can't hear you again, sir. Oh, Prof has been kicked out, cool? Let me look for Prof. Oh. So this class is very interesting. I see people like Wangi are just following it and having great fun. Hmm. Yes, Prof will share the calculation. We'll press on him to share the calculations with us. Right. Okay, the class is interesting. No, exams, okay, well. Adult school na your mate. Adult school no be anybody mate. So let me keep looking for Prof. As soon as it comes up, I will add him back to continue from where he stopped. Adult school no be anybody mate. So
Hello, sir.
You made a mistake on class. Oh, I think we should end the class and wait for the afternoon section. When Prof will continue with us. Yeah. So someone is still using TechnoSpark 5 here. So I think we can end the class now. And I left an instruction on the group. One of our professors sent in that instruction. Please look at the instruction. If your name appears on that list, send me your name and your phone number and maybe your email. Yeah. Thank you very much. There's an instruction on the WhatsApp group. Thank you. Let's call it a day now. I left an instruction on the group. Check it. If your name is there, do the needful. Let's call it a day. We'll meet by